All right, so we're going to take some notes on radicals. So when you have an answer in the square root, so if I ever ask you, leave it in exact form. So you're doing Pythagorean theorem, you take the square root of a number. If I want it in exact form, you just leave it as the square root. So sometimes it's convenient to leave square roots in radical form, meaning it has like radical form means it's left in this form. Instead of using a calculator to find the approximate. So instead of 4.82739 blah, 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 blah. I want it left in the radical form, square root. What we need to do is we need to look for perfect squares that are factors of the number under the square root. So let's just remind ourselves, what are perfect squares? So they give us the examples 4, they did leave out 1, right? 1, 4, 9, 16, 25, 36, 49. The reason we call them perfect squares is because 1 squared is 1. If I take the square root of 1, I get 1. 2 squared is 4. If I take the square root of 4, that's really saying the square root of 2 squared. Those cancel, we just get 2. 3 squared is 9. The square root of 9 is really just the square root of 3 squared. Those cancel, we get 3. Okay, hopefully we kind of remember those. So let's take a look at an example. So we're going to try to take the number that's underneath the square root and we're going to think, what are the factors of that? And specific factors I'm looking for are perfect squares. Sometimes it's not possible. Sometimes there's not a perfect square in there. 90% of the time when I ask you this, there is going to be a perfect square. So they give us the example square root of 9. So square root of 9, like I said, square root of 9 is 3 squared. So 3 squared, 9 is just going to give us 3. Let's look at square root of 18. So square root of 18, so I know it might sound a little confusing right now, but hopefully this step will work. Okay, square root of 18. 18, I want to find factors of 18. So I could go through my list. Okay, 1 and 18, okay, none of those. So 1 and 18, none of these are perfect squares. 2 and 9. 2 is not a perfect square, but 9 is a perfect square. So I'm going to rewrite this. I'm going to rewrite the square root of 18 as 2 times 9. So the square root of 2 times 9. What I can then do is I can separate these into 2 separate square roots. So I can separate into the square root of 2 times the square root of 9. Square root of 2 doesn't give me anything, so that's just going to remain. But the square root of 9, oh, sorry, I was thinking ahead. The square root of 9 does give me something. The square root of 9 is just 3. So times 3. So this actually is going to be 3 times the square root of 2. And you can check this. If you type into your calculator the square root of 18, enter, you'll get some decimal. And then if you type in 3 times the square root of 2, enter, you should get the exact same decimal. So the square root of 18 is 3 times the square root of 2. For your answers, I do not want that decimal form. I want everything in a radical form. We call it simplified radical form. So I want your answers to look like this. All right, let's try it with another one. So I'm just going to clear this. So let's try it with 80. Let's try it with 80. So I'm going to ignore what they have over here. And I want us to try something. So let's say I want us to look at 80. The very first thing that I usually do is I see, okay, is it factorable by 2 or 3? Because that might draw out what the perfect square is. So is it factorable by 2? Yes, it would be 2 times 40. And then I can go from there. 40 doesn't have that perfect square though. I bet you there's something inside there. Some people might look at this and automatically know, okay, 80 is divisible by 4. So then that would be square root of 4 times 20. So let's just go from there because I just want you guys to see this. So once again, we can break it up. Square root of 4 times square root of 20. Square root of 4, look on the top of that sheet, we see that that's 2. 2 times the square root of 20. But something's bothering me about that 20. I'm thinking that, yes, there is a perfect square inside there, and there is, right? 20 can be broken up into 4 times 5. So I would have to do this again. I'd have to set this as the square root of 4 times the square root of 5. Square root of 4 is 2, so it's 2 times 2 times the square root of 5, which gives me 4 times the square root of 5. Now, if I look back to how they give the example, they automatically knew, like they went through and they said, okay, it's the square root of 16 times 5, because 16 times 5 would give me 80. So sometimes, and I just wanted to show you this way because I think we are going to want to do, oh, 4 is the first one, so I'm going to use 4 right away. And you can do that, just know you do kind of have to look at what's still in the square root, and you kind of have to toy with it. I think that there could be another perfect square inside there. Let's take a look at another example. So I'm going to look at this one right here. So it's 3 times the square root of 98. So square root of 98, I'm going to start to think, okay, does 2 go into it? Yes. That would be 2 and 49. And lo and behold, 49 is my perfect square. So it's 3 times the square root of 49 times 2. Well, I can separate those square roots. It's still the same thing. Square root of 49 times the square root of 2 is still the same as what's up over here. Now I look at each one. Okay, square root of 49, that's just 7. Square root of 2, it's still just the square root of 2. But then I have that 3 that was being multiplied in front of the whole thing. So 3 times 7, 21 times the square root of 2. Checking your calculator, is 3 times the square root of 98, does that give you the same answer as 21 times the square root of 2? So we've looked at when I just have the square root and how we can simplify it. So we call this a simple radical form. When I have a number being multiplied by a square root, that's what we just did. Let's look at if I were to add or subtract the square root. So add or subtract. And I'm going to send you guys this video so that you can go through if you need to. So I'm looking at the example that they have, square root of 45 plus 4 times the square root of 20. Now, some of you might just do this. Oh, that's just 4 times square root of 65. No, you want to treat this, I need to have the same square root if I'm going to combine them. So I need to have the same square root if I'm going to combine them. So I need them both to be the square root of 5 or the square root of 6. I don't know what they're going to be. So let's just start, we'll work on this one. So trying to think what goes into 45. Does 3 go into 45? I always start with, is it divisible by 2? Is it divisible by 3? No. 5 goes into 45, and that would be 5 times 9. 9's a perfect square. So I'll get written out like this. That's the square root of 9 times the square root of 5, so I can break them up. Square root of 9 is 3, and square root of 5 is just 5. Now let's move over here. So I have 4 times the square root of 20. We actually already did this one when we were working on the square root of 80. That's 4 and 5. Those are the factors. So 4 times the square root of 4 times the square root of 5. 4, right, times the square root of 4. Square root of 4 is just 2 times the square root of 5. So now I'm at 8 times the square root of 5. And you can check that. Is 4 times the square root of 20 the same as 8 times the square root of 5? So right now I can now combine them. They both are going to have a square root of 5. Here I have 3 square roots of 5, and here I have 8. So I have a total of 11 square roots of 5. Notice, once again, all of my answers are in the simplest radical form. They have that square root there. I do not want to see any decimals. If you give me a sheet, even if you try to pass one off using a decimal, I'm going to hand it back. And then it's going to be late. So make sure you guys are checking with this. The last thing we're going to talk about, last thing I want to talk about is, and actually, I'm going to give you guys time. Let's take about 10 minutes, work on the first couple of problems. So I've really done a lot of them with you, so a lot of examples with you. And maybe in like 15 minutes we'll stop, and then you can look at the rationalizing the denominator.